the story.
Okay. Yeah, I went to the Shanghai Disneyland last week, and I'll show some pictures I took. Okay, this is the entrance of Disneyland, and we can see the weather in Shanghai was very perfect that day. And okay, this is awesome. And this, you know, the Lena Bella, Lena Bella, yeah, okay. Lena Bella is a new IP image of Shanghai Disney, and maybe it released on the September this year. And she is a pink Stafford fox, the girl, and she's very popular. So we can see so many tourists crowd around to look at her. And I took, and this is door model. Then this is a carousel model, and the visitors can go up and see it. And this is a motorcycle roller coaster, and cause I'm very afraid of weightless games, so my partner played this game, and I didn't. Then I watched the Frozen musical show. We can see this is the Elsa princess. Okay, and I took a picture with the castle. Yeah. Yeah.
3 seconds of delay when you show. So
okay.
Too fast, because your voice is in time. Photos are normally 3 seconds.
Okay, I know. Then, okay, this is a castle, and as the night falls, the light makes the castle more beautiful and dreamlike, and very colorful. Okay, this is castle, and the castle from the different angles. Okay, different angles, and I took a picture with the murals inside the castle. Okay, let me see this. Okay, this is castle, and this is carousel at the night. Is very romantic. Okay, the tree is already here for Christmas. This is a video about the fireworks. I'll play it last. Okay, this is the fireworks. Then the second day we went to the table tennis museum. This museum show us the development and the history of the world table tennis and the Chinese table tennis. Then this building is the Shanghai History Museum, and it shows us the development of Shanghai from ancient to now. At night we went to the Bund. We watched the night scene on the Bund, and we can see this the left building is the Oriental Pearl Tour, which is the TV tour of Shanghai. Okay, and this is the commercial street next to the Bund, and that's about the pictures. Then I'll play the video about the fireworks. Okay, I'll open the voice. Let me move on from this video is too long, and I move on. Okay, wait. Oh, let me see. Okay, from here. Loud. Okay, it's finished. The fireworks were accompanied by music and projections of Disney animation. And this show is very powerful and romantic. And I hope everyone has a chance to see the Disney fireworks with your beloved. Yeah, that's about my photos and about this trip. Okay.
Okay. Yeah. Had a project meeting online when she was visiting Disneyland on Friday. It's pretty good. Okay, I heard that the ticket is very affordable, so it's about $40 per person. So I think it's okay. Okay, so Arka, could you share your screen and then
Yeah.
let's dive into machine learning.
Yeah. Is my screen visible and am I audible?
You're audible, but your screen has not been shown yet. I think it has maybe 3 to 5 seconds of delay.
Just give me a minute. Yeah, now it's visible, right?
It's visible now. It's visible now. Yeah. Please show full, and let's get started. But I do think you have 3 to 5 seconds of delay.
Yeah, like I think there's some network problem. My computer is getting stuck. I'll just rejoin once again. I'm facing some problems. I'll just rejoin once again.
Okay. Not yet. I think it will show in a couple of seconds.
So I won't go into the slide because it's creating some problem. Is it okay if I just show it like this way?
I cannot see. Yeah. Now it's okay. Yeah, go ahead.
I don't know, for some reason the problem with the PowerPoint and it keeps crashing. So today, so I'll just start off. So today we will read this paper which is about predicting geothermal heat flow in Antarctica, and it is by Mareen Lösing and Ebbing. So a bit about the author. She did her BSc in geophysics from Munster, University of Munster. Uh, she also did her MSc in geophysics from University of Munster in 2018, and she's continuing her PhD since 2019 at the University of Cale.
Arca.
Her research in yeah,
Now
is the
okay. It was dark.
Acha, then I'll join my mobile. I'll just skip it because it keeps crashing. I'll join from mobile. I'm sorry for the delay.
No. I mean, you could keep your computer like this. Arca.
Yeah, go. Please say.
You could send your PPT to me by Slack. I could share it on your behalf.
Yeah, I'll do that. Now, Professor Zhang, I have sent you the PPT. Yeah. So I'll start. Am I audible? Okay. So this is about a bit about the author. She did her BSc in geophysics in 2015 from University of Munster. She continued in University of Munster and did her MSc in 2018 in geophysics. She is presently pursuing her PhD at the University of Caen. Her research interests are in geothermal heat fluxes in Antarctica, probabilistic inversions, glacial isostatic adjustments, and climate change. Can I just go to the next slide? So before we start off, I'll just take a few seconds to say what is geothermal heat flow. It is nothing but basically the heat energy which is being transferred from the Earth's interior to the surface. It is being termed as geothermal heat flow. Now, why this is crucial especially in the continent of Antarctica is that the geothermal heat flow is a crucial parameter and it affects the dynamics of the overlying ice sheet, like it controls its basal melting and the ice rheology over there. So we can use this to study the various processes that is happening or has happened in Antarctica. Can we go to the next slide, please? So a brief introduction about the paper and this work. So in Antarctica, the geothermal heat flow parameter is very poorly constrained. It can't be measured very accurately because of the thick ice sheets, and the data availability is very less. So what the previous publications they did some statistical analysis, they did some statistical modeling, they did some extrapolation and interpolation. So, however, they were not very useful while studying this GHF or geothermal heat flow in Antarctica. So this paper actually uses machine learning to make the same model that have been done previously. So, like I said, that geothermal heat flow affects the ice rheology and controls the basal melting of ice in Antarctica. So it's important in this study. However, in situ measurements in Antarctica, or rather in a lot of places, have their difficulties. Like they can be affected by local hydrothermal processes. They can be susceptible to climatic variations. So these things are a challenge while measuring them, even if someone wants to go there and measure it. Thus, to establish a continent-wide flow model, the authors of this paper have used various geological and geophysical parameters, uh, and they refer as indirect methods like tectonic settings. So, what were the geological parameters? They were mostly the tectonic settings, the seismological data, so on and so forth. Next slide, please. So, before we go into what they did, I'll talk a bit about their data set and their availability. So, they did for the target values, they did an XGBoost model, but what they did for the target values, they took the GHF data or the geothermal heat flow data, which is a compilation from 3 datasets. In the paper, you will be able to see that there's a geotherm.org, that's an open dataset, and there are a few other works that they had taken. And as for the predictor variable, what they had taken was a number of geological features which are linked to the GHF values. On the table in the right hand side of the screen, you can see the features. There are around 12 features and the papers from which they were taken. Next slide, please. So they do make a regression model that links to the complexities between the heat flow and the geological environment. I'll talk later how it is important in this study or what it gives us, the results. So they did use gradient boosting regression, that is XGBoost. Uh, I don't know about the exact number of data they used. However, it was done in a typical 80-20 ratio that test and split was done. And the final model was evaluated based on RMSE square and the R square values. And in the paper, and surprisingly, we'll see that the RMSE square value or the R square value or the normalized RMSE square RMSE values are very poor, but they have their own reasons to justify it. Uh, to the next slide, please. So this is one of the there are 2 diagrams. The figure A, they reflect the relative importance of the 12 features selected by the authors, and in figure B you can see that depending on the features, how the evaluation parameters they differ. So they didn't take so what they did was they first started with the proximity of volcanoes related to the and its respective geothermal heat flow gradient, and and then they took the next best one, that is the Moho and the lab, and they moved on till they achieved a better RMSE square. They didn't take all the features at once. That is the way of doing the feature engineering over here. Next slide, please. So the problem with creating a continent-wide model for Antarctica was that the data was not very much available. So they did one thing was that they took data from places that was the data was available. So they took it from Australia, their target continent, and they made a model to be sure of that it can be applied to a scale as large as the continent. So these are the results from their first test run, which shows the we can see that the predicted values and the actual values lie quite close to each other over a line, and the blue dots over here. So there are 2 kinds of data over here. The red dots, they show data or the predicted values whose training set included all the global data. applied over Australia to predict the values, obviously. But the blue dots, they show data. Sorry, wrong way. The blue dots show that, but the red dots, they show the data that was only calculated, only collected from Australia and used in the training set. So this is their base model on which they have developed their Antarctic model. Next slide, please. So for the heat flow prediction in Antarctica, the overall heat flow predicts a higher flow in the Western Australia than in the eastern part of the continent. And this is in concession with the other works which show that there is a ridge between the heat maps between the western and the eastern part of the continent. Just a second. Most of the available data fit well with the model. And what one more thing that they did, that they studied the relative importance of the features. Now this can act as a corollary to understanding that which feature plays more importance in controlling the heat flow in and around the continent. So for example, if there is a volcano nearby, obviously the geothermal heat flow will be higher. So we will see more about how they fine-tune various features in the later part when we discuss more in the discussion section of this presentation. But this is one more indirect output of the work that they have done. Please to the next slide. So this is the predicted heat map of Antarctica. That is the result. Actually, the circles, they show data that was actually collected from Antarctica, now from previous works. So what happens is that from this diagram, it is not very clear, but they also did one thing, is that they studied in the supergroup Gondwana, they studied the neighboring parts, that is parts of Australia, parts of India, parts of South Africa, and they studied and they showed that the heat flow map is in conjunction with the other continents in the supergroup. So that was one more way of them asserting that this model is a pretty good guess of what they are doing. Next slide, please. So this is their final model statistics. So this is the result between their. I have taken a direct screenshot from the paper itself. So this is a fit between the actual and predicted heat flow values in Antarctica, and the relative importance of the features. Uh, you can see that the features, what we showed for a general model, like by just typical feature selection, doesn't work quite well for Antarctica. So if you just remember a few back a few slides, I showed the feature importance of while plotting global data sets, global geothermal heat flow maps, the feature selection order is quite different. For over here, for example, volcanics, tectonics, the Moho, they have a higher importance. Next slide, please. So the first fit for Australia shows a close fit with the expected and predicted values, like I've just shown. Uh, so this gave them the confidence that this model can act as a base for modeling Antarctica, GHF of Antarctica. In case of Antarctica, however, there was a difficulty that values greater than 90 milliwatt per meter square showed a slight colder estimates. They do give a reason for this in the paper, but I found, since I'm not from the geophysics background, I did find it difficult in understanding, which we can obviously discuss later. Next slide, please. But apart from that, their fit was quite good. So what they did was, while choosing the features, they started with the feature with the highest importance. Now they kept adding the features one by one and saw that what happens to the RMSE values, normalized RMSE values, or the R square values. and that way they decided the feature selection. This was pretty interesting because that showed that depending on how many features, the order of features they're inputting, they're giving in an input as input, how their model changed. So one of the things that they didn't do, like I said in the previous, that their R square values, they're not very great. Like they have a 29% error in their model. But what they say is that they could have used an increased amount of global data sets in their training set, and extrapolated data which was not actually available. Just give me a second, please.
Actually, the previous, the feature importance now that is all very low.
Yeah, just a second. I just had a few people in my room. So yeah, sorry. So yeah, so what they did was that uh yeah, to the previous slide, please. To the previous slide before this. So they didn't go for an exaggerated database, which would have made a better model in case of global prediction, but in case of Antarctica, they doesn't do any good. So in their algorithm, the proximity to the nearest volcano and the crustal thickness are pretty good predictors with high training and test scores. Whereas if we see tectonics, they give contrasting predictions and yield a poor model score. However, it had the highest R square score, that is indicating that the predicted value and the actual value was quite close while we just took tectonics in question. So this is where the XGBoost modeling that they have used comes in play. It is unlike a normal regression model, which is a direct combination or direct predator versus target model. This actually keeps on iterating the trees that it creates till it gets the best feasible model. So it is not a direct linkage between a predictor and its target variable. Rather, the model is quite successful, or as they claim, is quite successful in linking the complex importance or complex participation of all the features on a large spatial scale. To the please, the next slide, please. So this is what I just said. To the next slide. We can skip this slide. I just said this. Okay. So this is basically the heat flow prediction of the Gondwana framework. So if we, what they did was to see that whether the Gondwana framework, because they shared their boundaries, Antarctica shared its boundaries, they tried to see whether the heat flow models show a correlation or are pretty much in lieu with the results. So this is one indirect uh, way they claim that their model is pretty accurate. Next slide, please. So in conclusion, this machine learning gradient boosting regression is a suitable approach for prediction of geothermal heat flow, as they've proved in for Australia and largely unknown contents of Antarctica. So one more thing is, while they work in conventional methods, is that, well, you are going for a spatial span, not all the data for geophysical data, they are not all corrected in the same method. So combining them, because every method has its own sensitivity, combining them can lead to some errors. So this can be avoided while using this model. This particular model for geothermal heat flow in Antarctica incorporates all the measurements and considers all the information of 12 geological and geophysical observables. So this is pretty much their work. Their work is not very much about uh, how what the mechanics or the geology or the geophysics, but their work is more about how to fine tune the various parameters, how to select the various features while predicting a geothermal heat flow in a continent as desolate as Antarctica. So it is quite a technical paper rather than a conventional paper of geology or geophysics dealing with, okay, this is happening, so this is the result. That's not what this paper was after studying. I felt, and there were many parts which I felt as not being a student of geophysics, I faced difficulty in understanding. So there were parts. So may not have conveyed the best out of this discussion. Anyway, that would be all. So thank you, and to the next slide. So this is just a last picture to show that how their model actually is quite in correlation with a few other established models. So this is a heat map picture of Antarctica they have given, and that I've just added in the last. Yeah, next slide. Thank you. If there's any questions, I believe there will be a lot. Uh, that's all.
Okay, thank you, Arka. So any questions for our participants? Actually, I have a quick question. So let's take a look at this. So basically, it also shows us that none of the features is so important, right? So none of them.
Yeah.
Sure.
So, yeah, go ahead, please.
So volcano that you likely to be relatively high, right? Then you should have high enough geotherm to, let's say, melt, keep the melt. Okay, I have a quick question too here. So when they, let me see, when they go back to Australia model, so when they map for the rest of the part that they without the real measurement, because all the circles here, I bet those are ones with a measurement, and for the part in areas that are without the measurement. So they create this shadow areas. So what's the spatial resolution when they create it?
Yes, they use some kind of again, that is a technical part that I didn't understand, but what in layman's term, I think that they did some satellite imagery to, and with some geophysical data, they tried to simulate the heat map of those areas.
So the geophysical data, you mean seismology data?
Yeah, the seismology data.
Okay. I think for heat flow is reasonable to use to expect that the gradient, because basically it's a temperature diffusion process, it's a heat diffusion process, because in some areas of high temperature, then it drops when it goes to lower temperature, and therefore the heat diffuses. So it's reasonable to put this type of a gradient map onto it. But I don't know what's their finest resolution though. Okay. Any questions for other participants?
Yeah, I have a question. So the test, so their test data is the real measurement of the heat flow, right?
No, not at all. So their test is their test is global data set. So that doesn't only include real measurements. They have like in a part of the paper, they say that they tried incorporating results from other papers which predicted the value using statistical measurements. Now, this went well for most of the places, but there's a particular place that is the ridge I was talking about in Antarctica, where if they incorporated that data, this predicted data from previous literatures, uh, it was quite the temperature predicted or the heat predicted was quite high and it was quite warmer. However, when they reduced it or they moved that data, so uh, what happened was that it predicted a pretty cold temperature, like contrasting to each other. So what when they had measured the differences, so where there is no difference while they're kicking out the predicted results and they're keeping the predicted results, they took those data. That is what my understanding is. But where there were, they said that in these places, the tectonic features are quite different, and it can't be. These places can't be predicted using what they said is that these places using their 12 parameters they have taken. So their training data set is a bit hybrid data set, and it's a combination of the three data sets, which I didn't take a look at the actual raw data sets. I think it is available. They've provided the links over there. Uh, so it's not a pretty much direct results only that they have taken. They have taken, they've considered the difference. If they take the direct measurements and if they take the predictor measurements, is the difference large? Then they have kept it up.
Okay. Okay, thank you.
Yeah. No, to answer Urmidi's question, they actually didn't talk about it in the paper. Their methodology was quite different. What they did was they took one of the parameters, which is conventionally the most important one in case of predicting geothermal heat flows, and then they just set the other parameters. They kept what to say, like hit and trial method or like bagging methods, and they kept it until they got the perfect combination which gave them the highest score. They selected it. But as for your question that whether there is any difference uh, in Australia and Antarctica, I don't think that I have seen that in the paper. That was my answer to Urmidi's question. In the chat, she had written a question.
So Luyan is asking that have they mentioned why Moho depth is so important for the heat flow regression result?
Yeah, they have. I'll just go to that. Now, again, for while they're saying the moho and the tectonics, they are not referring to like just they're taking that, okay, this is the tectonics, like this needs to be cleared out. They are talking of certain models that they have taken. It's not over here, it's in the paper actually. They had written a paragraph on it, but again, it was uh, something that I couldn't understand. I'm sorry to say, because again, I don't have a very good understanding of geophysics again.
Hi, Aga. I have another question. So did they get a final, score of their prediction of the their final model? They just
Yeah,
show in figure 4.
yes, the
value.
final model was that this model predicts with a error range of 29%. This was their conclusion, that the percentage of the error, that if you are using this model to predict the heat flow, there's a high chance that you will get an error in the margin of 29%. That is 0.29 is the RMSE value, normalized RMSE value.
Okay.
Actually, to me, it's also quite interesting here because I could see the lithosphere as the thermosphere boundary, the LAB. For that depth, we could regard that below that depth is all mantle adiabat, so it has a very similar temperature. I suppose we could assume the global temperature at the lithosphere as thermosphere boundary could be similar. So to me, that is a little bit counterintuitive. So whether this layer is too deep or not, it doesn't affect much on the Earth's surface.
Okay,
Because
so
this depth is much deeper, then you have much thicker lithosphere for the heat to conduct through. So likely that will result in a lower geothermal. But not for MOHO though. MOHO is the other way around. That's way more important than that. Okay, go ahead. Okay.
so they did one thing again, that while considering the other features, like if they had started with volcanoes, tectonics, ridge, young rifts, everything, they had done all that for a particular moho and lab. So, and they considered the moho and lab in a different set, like while considering its importance. So while, let's say, the 10 features, remaining 10 features, their values, while they were being put in, they were always from a particular moho, or like the depth and lab. Like I couldn't get a clear idea of it, but this is something they have done, that the other features are in relation to the lab values and moho values.
Because the other thing that I could, from my interpretation, that the MOHO value matters, that for the crust, is enriched in radioactive elements. For example, potassium, for example, is concentrated in the crust. And these heat-producing elements, generally, then they could produce more heat.
Yes, that is the conventional idea that we have, that because of the radioactive decay, heat production is quite high. Like that is one more thing. Yes, is that theory based on figure 4, which is figure, okay, but the score, no, the figure 4A. Like, are you suggesting this score from this paper, or like are you suggesting from the previous diagram that I had shown? This is a question for Ben. Like he asked a question in the chat.
Okay, so I mean they analyze this feature importance, right? But they get this feature importance based on the 0.44 Arfang scores. So is that reliable or just
No, like are you saying it from the paper, like by reading the paper, or from the diagram I have shown? Because in the diagram, the R square value that they are showing is not for Antarctic. It's there was a previous diagram, it's just a couple of slides before. This one.
Okay.
Next. Not previous, like later ones.
Yeah.
The one after this. Yeah, this one. From here, are you saying it?
Okay.
So this is not for Antarctic. This is for Australia. So for which are you saying? Like 0.44? I couldn't get your question.
Okay,
Okay.
yeah, it's 0.4, but it's not that good neither.
Yeah, and they give a pretty it's a strange argument that they've provided that they don't need to actually make their model statistically sound because they have enough other reasons, other things like the Gondwana supergroup heat flow map is quite in correlation with the junctions in which Antarctica was in touch with. Then they provide that the other predictions that the actual values which have been collected from Antarctica are in correlation with their predictions. So these are the reasons that they give to say that they don't need to make a more statistically sound a model because that would be overfitting, which is constrained by their model because it's a boosting model, so it's constrained. So they don't want to disturb that. This is the reason they give for not going for a further better score with a more better data set or better feature engineering. And I don't know how convincing is that, but this is what they state in the paper. And could the predicting result from Australia data really cover Antarctica? Why they focus on Australia data? Is there something strong relationship? I don't know about your first question. That okay, because they don't. They just do it in Australia to for the spatial span in terms of a continent. I have no idea about the areas. Uh, as far as why Australia, because again they were the part of the Gondwana supergroup, so there's a chance that yeah, and their present locations. So that I might say. But the first question, yes, I also asked myself that like if I am making my best model on a different continent, how will it work on another continent with a difference in climatic conditions and everything? Because while they're taking the in situ measurements, they're highly uh, favored or highly like influenced by the climatic conditions, the local hydrothermal processes. So that is one more question I also asked myself. So I can't answer that. But the second I think is pretty much because of their supergroup structure.
Actually, I should also point out that Australia is an interesting place in terms of geology. It's a very old continent, and also Australian government is really insisted on open source for the all kinds of data that collected by universities and even by the Australia Geological Survey, etc. So actually, I did get to check their website to see that basically we could download the geochemical analysis for sampling all over Australia. I think it's by maybe 10 kilometer by same kilometer pixel. Then you could get some elements mapping throughout Australia. So that's actually one great thing in Australia that people have done. Although not for all elements though, but for some elements that people have already done that. So it's a very good example that how the international geology community that should do to open all the data, all the source, all the data people measured and make them open source. Okay, I think that's about it for today. And thank you very much, Arka, for giving talk, lead discussion, and we're going to see the speaker on Wednesday. And let's see how it goes. Okay, great.
Yeah, thank you all for hearing.
Okay, thank you. And thanks, Lei, for taking us to Disneyland online. Okay, bye-bye.